Hello, thanks for coming to my talk. My name is Charles. I'm a production engineer at Shopify. In production engineering, we basically keep the platform running so that our merchants and customers can keep selling things. So how many people actually heard of Shopify? Oh, that's good. What we do is we provide a platform for merchants to be able to sell things online. Nowadays, we have multiple channels. You can sell things on your online website. You can sell through Facebook store, sell on Twitter. And we're based out of Ottawa in Canada. And that's a picture of what it looks like when it's not minus 30 outside. And here's a history of Shopify as told by emojis. Our CEO, Toby, he came from Germany. He came to Canada looking to sell snowboards online. Then he realized that there is nothing off the shelf that he found that he was satisfied with. And because he's got a programming background, he decided to write his own online software to sell snowboards. And at the time, he picked something called Ruby that was relatively new back then in 2005. And he built a store that he was then able to sell his snowboards online. This is probably an outdated photo of all the employees at Shopify. Right now, we're about 1,500. And this is Flo. He gave this same talk on Wednesday at Velocity, New York City. And this is me. So back in 2004, Toby created a shop called Snow Devil to sell snowboards. But he didn't have much luck selling snowboards. Then he realized that what he built for Snow Devil, other merchants can actually take advantage of and use it. So in 2005, we started to be multi-tenant. Before that, it was only Snow Devil by itself. And between 2005 and 2012, things went okay. We grew. No big technical changes until in about Black Friday, after Black Friday 2012, we realized that at the rate we're growing, we can't take the load of Black Friday in 2013. At the time, and actually we still do, we seem to be handling double the traffic every year. So our performance team worked about a year in 2013, before 2013, in Black Friday, we actually sharded for the first time. So in 2013, we had 2 shards. And in 2015, we created a second data center. And in this year, we're actually trying to make it active. So one of the problems that we have to deal with at Shopify is flash sales. Does anyone know what a flash sale is? Anyone bought something from a flash sale? Yeah. So typically, a flash sale is a shop where they don't usually have inventory listed to be purchased. And they typically have limited quantity available. And they will, through various means, advertise that, oh, you can buy my product at this particular time, and we don't have that much stock, so you have to buy it quick, or else you won't be able to buy any. So there is this person called Kylie Jenner. She has a shop called Kylie Cosmetics. And she has flash sales on our platform. And if you looked at the kind of the top right corner, She has 16 million Twitter followers. And her sales model is basically you can't buy anything from her shop until she tweets about it. So what do you think that happens? You have 16 million people all hitting our website at the same time? Yeah, that's a little scary. And we think it looks something like this. And if you look at our metrics on our low balance of throughput, it looks something like that. And you can see at the bottom of the chart, that's our kind of baseline day-to-day load. And those big, tall charts are when a big store has a flash sale. So that's obviously a huge problem. In the beginning, we didn't handle those sales well. A couple of years ago, when one of our larger merchants had a flash sale, it frequently took us down. And obviously, that's not great. Because we're multi-tenant, it went down for everybody. And we had the option of kicking them off because they weren't paying us that much. But we decided that this is something that is worthy to solve. So rather than kicking off this merchant and say, sorry, we can't handle your shop anymore, we decided to put some effort in and try to solve this problem. And I think these days, at the most part, we have solved the problem, and Shopify kind of has a reputation to be able to absorb these flash sales. So summarize the problem, which I'll tie in later on in the presentation. These flash sales can happen at any time. The merchant doesn't have to tell us. They can just say, OK, I want to sell X number of things at this time. But the larger merchants these days actually does communicate with us, give us a little bit of heads up, which we really appreciate, to make sure that we have the capacity available and people around in case something went wrong. And as you saw in the previous chart, these sales really test our capacity. So we have to be always massively provisioned. And you can't just rack new servers with 5-minute notice, right? So handling these issues, it's a challenge. And these flash sales can really go on at any time, and it will last a couple of minutes. So we just talked about how Shopify went from one single shop to multi-tenant. Why did we do it? Well, because it makes sense that we can add new hardware for every merchant, I suppose. But that's obviously something that we can't keep up. So there are a couple of ways of doing it. Obviously, we have the left side, like we talked about. We can provision new hardware for every new customer we have. But right now, we have over 300,000 merchants. That's not plausible. Then on the other extreme is share everything. Just put all our customers in the same set of hardware. And that's what we did for a long time. Obviously, you can only provision a database so big before you cannot put any more load on a server. So sharing everything is really not a long-term solution. So here's kind of a scale from share nothing, which is what we did in the very beginning in 2004, when we only had one shop, to share everything, which we did between 2005 and 2012. Then we did some work that put us further to the left. Then we did a bit more work, which shifted us kind of in the middle. But from just testing and looking at the architecture, we can tell that this isn't quite right yet. So we did some more work. And we think, for now, this is a good place to be. And we'll go back to this chart later on. So in the beginning, we had a small Rails application. We had multiple web workers, job workers, and one giant database. It was big, it was expensive, but it's single point of failure, right? Just one database. We did have hot backups, but if your master died, you went down. So in 2013, we added sharding. So we had multiple databases. And luckily for us, sharding by a shop or merchant did well. So based on your shop ID, we can assign you to a particular database. As you can see, that means every web worker, every job server has to connect to all of the databases. It works okay, which, given this model, our developers have to be shard aware. We have to realize that in your code, you have to do some sharding stuff before you can write your business logic. We lived with that. And then in 2015, we went multi-DC. So sharding gave us some scalability. We can shard across. But what happens if a tornado hit our data center? We'll be done. We didn't have anywhere else to move to. So it was important for us to be able to have another presence in a different data center. Why? We talked about redundancy, but first of all is maintenance. We would like to be able to do some maintenance and take that data center offline. And I don't know how many of you guys are in the cloud versus building your own data center, but our first one looked pretty messy, and it kind of grew organically. And we wanted to build a new data center so that we can actually clean up some of this stuff. This actually is not our data center. And as I said, what if something happened to the data center? We want to be able to move to it. So something happens, we move to the backup data center, and maybe we'll be offline for minutes, hopefully not hours, but we move. So when we built our second data center, it's semantically exactly the same. We have sharded databases. We have web workers and job workers. But we took the time to actually revamp our networking so that we don't have any single point of failures in our routers and switches. So we have a backup data center. Databases are read-only, and we replicate the database data to our backup. So hopefully at any point in time, if something happened, we can switch over and make that our primary data center. And once we fix the original one, we can then replicate data back to our original data center. And how do we do this failover? It's funny, this slide, because we had our keynote about landing a rover on Mars. We didn't do anything like that, but for a failover, the first time we did it, everything was manual. So we had a whole bunch of people sitting in a big room full of screens with every metric you can imagine on it. And everyone had their part, And it was kind of orchestrated that, this person does this, and you do this, and you do that, and hopefully nothing goes wrong. We did practice many, many times with a test shard. So we were able to run a test shard on our backup data center. But we've never really moved our entire production traffic to the backup. And if you ask people how confident that they will work, I think we're pretty confident. But we really, truly didn't know whether it's going to succeed or not until we actually did it. And the first time we did it, we had a few kinks here and there, but in general, it was a success. And doing it that way is kind of scary. So many people doing things manually. You have so many cases where someone can mess up. Someone can mistype something. So we decided to basically script everything. Can we take the human errors out of the system? So we wrote some scripts. And now our failover is just one script. One person can run. And we actually had an intern try it. I think he was a little nervous, but we said, it should be OK. We're behind you. It's easy to roll back. You just do a failover on the other direction. The whole process with this script takes about 5 minutes. Storefront traffic didn't go down, but we did have to take about 2 minutes of maintenance time where we had to switch database replication chains and make the new ones read-only, the new ones writable and the old ones read-only. So we took about 2 minutes where no one could check out on our platform, which I think was pretty good for actually moving our entire traffic to a different data center. So what's next? So now we have a backup data center. So in case something truly went wrong, we can go to it. But you have this whole data center sitting there doing nothing. That's kind of costing us a lot of money. And what if we move one of the shards over to the backup? Can we do this? Makes sense, right? At least this way, we can leverage some of the database resources. And you can still have a read-only backup. In case one database failed, we can always switch to the other one. And now we leverage the extra capacity of the web servers and the job servers. But this isn't quite what we want. So in 2016, this year, we kind of created the term, the idea of podding. We want to be able to isolate entire pods. So basically, we can have standalone systems where everything's enclosed. So given the pod, we have dedicated web servers and job servers and isolate the parts. So no one shop, let's say, can take all of our app server resources or the job servers. And we still can only have, each pod can only be active in one data center. So now we have different pods. So how do we figure out where a shop lives? Because for the longest time, we just have one data center and one set of load balancers and one set of app servers. So we leverage a thing called Lua. Lua is a language that we can run in Nginx. And with Lua JIT, the performance is really good. So we store basically the shop's domain to a pod ID in MySQL. Obviously, we'll cache that information when we can and have our Lua code be able to forward the request to the right pod. And other things we actually run in that Lua stack is sending our Nginx logs directly to Kafka. So we can do diskless logging for Nginx. We can cache shop pages on our load balancers. We can implement throttles with Lua. And this year we rolled out SSL for all shops, for all the domains. So we have 300,000 customers right now. So even if each shop has only one domain, we're looking at hundreds of thousands of SSL certs. And we use Lua as well to serve these 300,000, up to minimum 300,000 certs in Lua. And it's been great for us. So our next thing that we worked on is floating capacity. Because we've created pods, we've isolated everything, but if you look at this diagram, one shop now has less capacity than what we had originally. Because originally, before we had podding, any shop can actually use our entire resources for all the web servers, all the job servers for that shop. But if we were to put hard isolation between the pods, then you're limited to only those web servers and job servers for that pod. So we came up with the idea of floating capacity. I guess in military terms, maybe your reserve. These floating capacity is for when we notice a merchant have really big traffic incoming. So we can actually assign more of these free-floating capacity to that pod. So back to this diagram where we showed some of the pros and cons of sharing nothing and sharing everything. I think our current pods with floating capacity kind of is a good middle ground. So now we have multiple DCs, and we want them to run active and active. How do we do this? In a scenario where we only had one active data center versus a backup data center, we can use BGP. So let's say we want to move from the left side to the right side. We can advertise our BGP routes in the new data center, and then withdraw our routes from the old one. So that should steer the traffic from the internet from the old data center to the new one. But BGP is not real time. It doesn't switch everything over at once. So it takes a while, minutes. And there are cases where some customers would still go through the old data center because the internet routes haven't completely propagated yet. We do have a point-to-point link between our two data centers. And with our sorting hat Lua code, we can actually figure out that, oh, this particular data center is not currently active. We should send it to the other side. And that works out pretty well for us. And how do we scale our front load balancers? Our traffic hits our edge router, then sends the request to our load balancers. And the load balancers running our Lua code will figure out which pod that request should go to. Then how do we load balance our load balancers? How do we figure out which load balancer to send the traffic to? Why do you want to run multiple load balancers anyway? Well, obviously, we want to spread the load. If you have SYN flood attacks, you want the capacity to be able to handle those SYNs. You want to be able to handle DDoS attacks. We have quite a few load balancers right now. And what if one of them dies? You know, we want to be able to stay up. So how do we do it? For a while, we actually did DNS round robining. Works okay, but when something goes down, you kind of lose a fraction of that traffic. Now we actually use BGP. So we run ExaBGP in our load balancers, and we advertise one set of IPs from all those load balancers. And the router will use ECMP, equal cost multipath routing, using consistent hash, and be able to, for the most part, evenly distribute the load to all load balancers. So in this case, we have our original test case, use case where we only advertise out of one data center. Then we added a second data center, but that was just a backup. So how do we put a pod on the other one? What we do is actually do BGP Anycast. So we advertise our entire public errand space out of both data centers. And obviously, you can't control which data center your customers are coming in because of BGP routing. Your customers are going to take the shortest AS path to us. And historically, Anycast people only did for UDP traffic, like DNS. But we find that from day-to-day use, it actually works pretty well for TCP. And routes don't usually change that much from day to day. And this is actually working pretty well for us. And because we don't have control which data center traffic comes in, we have our sorting hat software on the router, on the load balancer, to be able to forward traffic that we deem to have gone to the wrong data center through a point-to-point link between our two DCs. So if traffic came into our left data center 1, but we want to forward the traffic to pod 2, then we forward that traffic through a point-to-point link. In the same manner, we can actually build network POPs. Basically, you have no app servers or databases. You just have load balancers. Useful cases is like we want to put network POPs in Asia or Australia and Europe to help with the latency, especially if you have traffic coming in from all over the world and your data centers are in the US only, then the latency is pretty bad sometimes. So if you put a network POP in Australia or Europe, then at least you can have that traffic coming in and going through your internal network, which you have better control of how much latency you have to pay. So Some of the things we discovered along the way, scaling our small Rails project to now running multiple data centers, serving 300,000 merchants. It's a fine balance between isolation and capacity. It's great that you can isolate everything, but then it's really hard to scale, or you really pay for it when you want to scale. So back to this chart. 2004, our one-shop situation. And in 2005 to 2012, we did this share everything model, everything in one giant database. Then in 2013, we added sharding. That moved us a little bit to the left. But realized that we can do more. And in last year, and continuing to work this year, we're actually moved to a second data center, and we implemented podding. Then we added floating capacity to help basically those use cases where we have lots of traffic coming to one pod. We want to help the cases where we need the extra capacity to handle those loads. And we think that is our sweet spot at this point in time. We use Nginx extensively in Shopify. We used to be on HA proxy. We moved to Nginx. And we write a lot of stuff in Lua, running Lua JIT on Nginx's. And we find the performance to be really good. I know that a lot of companies like Cloudflare actually does a lot of their WAF stuff in Lua in Nginx. And they can basically do a lot of their WAF rule testing in less than a millisecond. We use BGP and ECMP a lot of places within our network. It's great for basically doing load balancing. And if you have health checks for your BGP client, you can get it to either withdraw routes or have the BGP timer expire and withdraw the routes on the router. So we can do high availability pretty well. And lastly, this flash sale problem is kind of more unique to Shopify. I'm sure that the company that you're working for have issues that are causing problems. Like I said in the beginning, we could have kicked people off that caused issues with our platform, but we decided to buckle down and tackle these issues. And we came out better in the long run. So identify your problem and try to tackle it. Thank you. I guess I ran a little fast, so questions?
So it seems like in your architecture, the only non-redundant thing is that MySQL can hold those endings. So do you rely on caching for the recovery, or do you have a redundancy for that MySQL as well?
MySQL, we have sharding, so it spread out the hurt if something goes down. We don't have clustering just because the technology is kind of scary. You don't know when a failure happens, what behavior you're going to have. So we actually have a hot backup. It replicates the writes to the backup. And then we have a hot backup in case one of them fails.
Sure.
So we kind of have a single point of failure, but we don't have any magic solution.
Hey, yeah, just real quick. Maybe I missed it, but what load balancer are you using? Is that Nginx or is that something else?
We're using Nginx, yeah.
you showed the massive spikes you get from a flash sale where you're thousands of times it would appear higher throughput than what you are on a baseline. Do you practice that in non-production? Do you simulate load to see how it's going to hold up before you get to a production situation?
Yes, we actually do tests. We actually wrote a tool in-house called Genghis Kern with the Horde. What that does is actually simulates load by creating tons of requests to our platform. We wrote the code in Go with a Lua part where you can script the things you want to do with a test tool in Lua. And we don't have a test platform. We actually test against production. So we hammer ourselves.
All right.
We have to be very careful we don't DDoS ourselves. But for the most part, that works well for us. We actually have an automated test tool that runs periodically just to make sure that our performance haven't degraded while someone shipped something. Because right now, on a daily basis, we deploy code at Shopify maybe like 50 times a day. So we want to catch performance degradations at as early as possible. Alan?
Have you considered moving to the cloud? Because I think for the flash sale problem, the auto scale feature or the elasticity feature in the cloud may help in that case. And also, like your strategy for scaling the load balancer, I think that's already something available in AWS when they do their elastic load balancing.
Right. We do have some stuff in AWS right now, but the majority, our core stuff is in data center. We've done some investigation in the cloud for moving our production stuff in the cloud, but nothing concrete right now. But yeah, it's a good point. We can leverage the cloud for scaling up these capacity for app servers, but yeah, not right now.
Okay, for your multi-datacenter setup, you advertise the same IP on both data centers. So you have customers coming in the wrong data center, and then you're going over the internal link.
Yes.
That happens for the first request. Do you have anything to prevent that from repeatedly occurring? Do you have a different DNS that you reroute them to that's specific to each data center?
Yeah, that's a good point. No, we do just straight BGP Anycast. So we let basically our customers decide which is the best path to us. Obviously, going over the point-to-point, you're adding around 20 millisecond latency. But I think when we looked at the problem is, you may have paid that latency going through the internet to go to our right data center anyway.
Okay.
So it's hard to say whether it's a problem or not.
Okay.
Yeah.
Thanks.
A follow-up to that is, does BGP Anycast or any of the other technologies that you're using guarantee or make reasonable assurances that if somebody starts like a TCP connection for HTTP going to one data center, that it doesn't just some router somewhere in the middle shift to the other data center partway through that transaction?
That's definitely possible because we have no control of internet routing, right? But in practice, we haven't found that is a huge problem. And within our network, once they hit our edge router, we use a consistent hash algorithm for ECMP. So it's based on source IP, source port, destination IP, destination port, and the protocol number for the hash. So once you hit our router, it will be consistent to that load balancer. So we don't have that issue within a load balancer, but it's quite possible that some ISP somewhere changed their route, so now you're no longer going to that data center. That's quite possible. For those cases, the best we can do is hope TCP reset and you reconnect to the other side. But in practice, we haven't seen that to be a huge problem. All right, thank you.